Welcome to Black Hat 2015. Got a couple of quick announcements before we get started. There's going to be a reception tonight in the business hall at 5:30 p.m. That's located in Shoreline A that you can find on your maps. Also, the Pony Awards are going to take place tonight in Mandalay BCD at 6 p.m. If you haven't already, please turn off your cell phone, or at least shut off the volume so that we all don't have to enjoy your ringtone. And if you're not quite sure where you are, you're in Jasmine Ballroom. This session is Emanate Like a Boss, Generalized Covert Data Exfiltration with Funtenna, with our speaker, Dr. Ong Sui.
All right, thank you so much. A little bit about me, for those who don't know. I spent the last 7 years at Columbia University. I just graduated a few months ago, so got my PhD, and thank you. And I also co-founded and I run a security company called Rebel Security, where we focus on creating technology that secures embedded devices against exploitation. So I have 3 disclaimers. Okay, so the research presented in this talk is not funded by any government organization or Columbia University at all. The second disclaimer is research presented here has nothing to do with what we do at Rebel Security. This is really just for my academic curiosity. And the third one, which is the most important one, is I only pretend to know how electricity works. And I didn't know a lot to start with, but after this project, I know less now than I knew before. So, and I'll show you guys why, okay? But, you know, I have a lot of humans to thank for this work, but I have to thank some of the hardware that I used to get this thing off the ground. These things are awesome because, well, first of all, I got this guy, which is a geophone paranormal research tool. Right? This is something that you can buy on Amazon, and I have one that is designed to find ghosts. So we're going to use that for science. And there's only a single question on Amazon about this device. You think there'd be more, but it says, are these things from human voices, from alive people, or is it just like my neighbor or something? It's awesome. But we're going to answer this question, maybe on Amazon. The second thing is we created a homemade dog whistle detector, right, in a cup pointed at a printer, and this will make sense in about 20 minutes. And the third one we wish we can get, but it was too expensive. Anti-radiation shielded maternity panties, medium level protection, but it's incredibly expensive, so we didn't get that. Okay, so we took all of this hardware to do one fun little thing called Funtenna. So what is Funtenna? Funtenna is very shortly, malware that intentionally causes compromising emanation in the device that it's executing in, okay? A little bit more specific, it's software payload that intentionally causes the host hardware to act as an improvised RF transmitter using hardware that is not designed to cause any type of electromagnetic emanation whatsoever. And why would we want to do this, you ask? Okay, so suppose you had a thing, right? XYZ, it doesn't really matter. Maybe this is your laptop, your server, your phone, or routers, or printers, or TVs, cars, and even entire buildings, okay? This is what we want to do. We want to take a tiny little bit of software, inject it into the thing, right, through all of the ordinary methods of getting code execution into embedded devices and computers, right? And this is what we want the software to do on the device. We want this thing to emanate us a signal, right, that the attacker can receive in some distance away, and we want to encode some information, which is probably all your secret info, right? And that's what we want to do through software. And you'll ask, oh, and the receiver, well, the attacker will also need some cool receiver doodad, right? Super spy hardware. But if you're thinking, you know, why are you doing this when, you know, every XYZ thing on the planet now has all the different ways of communicating with the rest of the world, like Bluetooth, Wi-Fi, cellular, Ethernet. Okay, well, here's the answer. That's true. You can send information through all of these transmission mediums, but these are well known and they're monitored, right? So if you wanted to exfiltrate secret data through this, there's about, I don't know, billions of dollars of R&D and technology that stands in between you and getting that information out, right? So think about the firewall, anything that locks packets, anything that monitors traffic. We want to avoid that entirely. Okay, so we're not going to, and right, so if you can't avoid it, you become sad attacker, okay? But we want to be happy attackers, so we're not going to use any of these conventional transmission mediums. Instead, we're going to use a transmission medium of the attacker's choosing, and we're going to choose some things that you, the defender, are not going to be able to monitor effectively. And lucky for us, the attacker, right, we have all of the EM spectrum to play with. So we can start with something that's in the sub-acoustic range, right? This is where the ghost hunter will come in. And we can go slightly higher frequency and enter the acoustic range. And if we want to be a little bit fancy about it, we can do ultrasonic, okay? And then after that, we can hopefully hop onto all of the RF bands, right? And emanate information, encode it, modulate it, and get it out to the rest of the world where the attacker can hear. Okay, so why would we want to do this? Why do we want to go through all this trouble? Okay, so suppose you had a super secret fort, just like this one, okay? This fort is full of secret things and secret people with all sorts of secret in it, right? And you, the attacker, want to know all those secrets. So the most obvious way to do this, right, is get some malware in there and just have all the machines and all the things send information directly out to the internet using their network, right? But like we just mentioned, this is really obvious and you're going to get caught, right? Something, hopefully, at least a small portion of the billions of dollars of R&D and technology and products that's meant to find you, detect you, will actually capture this attempt. So you don't want to do this. And really, if we're talking about an actual super secret fort, right, there's probably an air gap where the thing's not exactly connected to the internet anyway. So what we need is some anti-super secret fort technology, okay? And I'm sure everybody here is seeing, right? Last year, we went through the AND catalog from the NSA, right? And I don't know what AND stands for, so I'm just going to assume it's like Amazing Ninja Tech, right? You look into that catalog, and this is what they recommend. Here's the way to do it. First, you get an intern, okay? The intern also will have a tiny little electronic component, right? That's called the retro-reflector. That's very small, very sneaky. And then the last thing you're going to need is something like the CTX 4000, which is a suitcase-sized radar generator thingamabob that does continuous RF illumination, right? And here's how you put all these three things together. Okay, step one, the intern sneaks into the secret fort. Okay, that's kind of hard, but let's go with it, right? You can do it. The intern did it. And step two, the intern physically leaves this implant onto a machine or device that we want to spy on. Okay, and then of course, hopefully sneaks out without being killed, right? And step three is the intern turns on the CTX 4000, right? And enables this continuous stream of RF illumination, which looks like this. It's basically a radar beam pointed at the thing that we want to hear, okay? And if everything worked well, and nobody got killed and nobody found out that you snuck in there and put the implant in, what happens then is the retro-reflector modulates the data using the energy from the radar beam, and then exfiltrates information which the intern can now have, right? So that sounds like a fun idea, maybe, but this is only a good idea if, let's say, you had infinite interns, right? And also you didn't worry about leaving physical evidence behind, right? Because you still have that physical implant stuck in the secret fort, and if somebody finds it, it's going to be pretty obvious, right? Like they're being spied on. But I guess number two is not a real problem because of number one. If you had secret, unlimited interns, you can get them to come in and come out, and that's not really a problem. But let's think about retro-reflector technology, right? It's very cool, but we have to put it into historical context, right? When was this thing invented? Why was it invented? And how was it deployed in its heyday? So the earliest example of a retro-reflector that I know of is the Thing, right? So this is a very cool piece of passive element that was hidden inside this plaque that was given to the American Embassy in Russia. This is circa 1960. The nice thing about this was completely passive, no active power source. You bounce the radar beam off of this little guy, and the diaphragm actually modulated the reflectance, and you can hear audio data or audio signal from that room, outside that building, right? But you had to shine a radar beam or RF illumination directly at the device for this thing to work. So this was very cool for back in the day, okay? But this was a phone back in the day, right? That was the phone that the retro-reflector was really meant to implant and spy on. But we don't have those phones anymore. We have this phone. Okay, and back in the day, this was, an office, right? We had your IBM Selectrix typewriter, and I don't really know what this little guy is, but I'm sure it's very cool. Yeah, but today, we have this office, right? We have computers, network printers, blah, 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 all connected to this network, right? So let's ask the question, what's the difference between this phone and this phone, okay? Well, the difference is this. There's about 500 million transistors, right? or more on the phone that we use today. There's about at least 1 million lines of code. And the big difference is the phone today isn't really a phone. It's a general purpose computing device, right, fit into a plastic cage or a case that makes you think that this works as a special purpose thing like a telephone or a router or whatever it is. So the next question is, can we leverage this difference to do better than RF retro-reflectors, right? If we wanted to sneak into the secret fort and get this information out. Right, we want to emanate not like a scrub, we want to emanate like a boss. So here's what we want to do. We want to exfiltrate data from using only software, right? We don't want to do RF illumination, we don't want to do implantation, right? We want to just get the software in and get the data out. And we want the software to run on all the things, right? So it's, you know, it's possible maybe to write a malware payload for a specific type of device, but it would really be great if we can generalize this and come up with a technique that would work on basically every embedded device out there. And we also want to be able to transmit this data on arbitrary frequencies using arbitrary data modulation schemes and data encoding schemes and potentially crypto, right, of the attacker's choosing. And lastly, we want this to all evaporate when we're done. So we don't want to leave behind evidence. We definitely don't want to leave physical evidence behind, but the software should just, you know, evaporate when we're done with the exfiltration, okay? So we can totally do this. The first part is we're going to take advantage of what we know about compromising emanation. And the second part is we're going to take advantage of, you know, some firmware shenanigans, which we'll talk about, which is the bulk of the Funtenna work. So as far as compromising emanations go, there is a rich history of research done in this area. You know, for example, Van Eck phreaking, right? You can actually reconstruct the content of CRT monitors from very, very far away by looking at the RF output of that monitor. And Marcus Kuhn took this to the next level by looking at things like LCDs and other things. And somewhere in the 90s, you know, we discovered that you can actually pick up an RF signal or FM signal coming off of UART transmission lines, so RS-232 console cables, right? And we're going to revisit both of those things. And you know, more recently, you know, we talked about acoustic key extraction, right? By basically listening to the hums of the capacitors of, you know, machines doing RSA algorithm, right? To pick out the content of our secret RSA key from something like 4 meters away. So that's very cool. This is, you know, what this setup looked like. But let's think about what all of these works have in common. Okay, so the majority of the history of compromising emanation research goes something like this. You take a very faint, accidentally leaked signal, right, from some device, right, and you use a very big, powerful antenna to try to capture that tiny little accidentally leaked signal, and you throw a lot of computing power at it to extract some computational state of the victim device, like an RSA key, or like data being transmitted on the RS-232 line, right? But what if we turn this on its head, upside down? Okay, so what if we take advantage or use software to create very loud, intentionally induced leakage of information using emanation, and we take this big, powerful antenna? You know, what can we do? Can we do better than, you know, getting an RSA key from 4 meters away, right? And if so, how much better? Can we do an order of magnitude better, or even more? Okay, so I'm going to show you the first demo. The first demo is an acoustic Funtenna emanation. So keep in mind, right, so, you know, think about the context of the Shamir crypto and key extraction example of laptop, RSA, you know, encryption, and tiny, minute amount of audio data coming out of it, right? That's software-induced acoustic output. So let me show you how much better we can do when we do this intentionally. Okay, so what we have here is a Phantom laser printer, which I'll talk about later. It's the cheapest printer I found on Amazon. It's not that great of a printer, but it's really good for making, you know, sounds and such. So let's run this payload. Okay, right? So this thing doesn't have a speaker, right? It's not meant to make sound, but here it is. So this is actually using Funtenna code to modulate down its own boot code down to the acoustic range, and it's playing it back to you. So it's literally singing its own boot code back to you, right? And there it is. So instead of tiny little amount of sound, right, we can create a whole lot of it, and that's the intuition for the rest of this talk, right? If we can intentionally create this emanation, we can do a lot better and potentially sneak out information at longer distances and at higher data rates. I don't know how PowerPoint works. Okay, and this is where the Ghost Hunter tool came in, right? So not only can we do acoustic, we can do sub-acoustic. So this is the geophone, hooked up to baud line into my sound card. And over here you see some, we definitely have signals in the sub 1 kilohertz range, okay? And the setup looked like this. This is my messy desk. This is the printer. And over here is my Ghostbuster thing, right? And it does propagate fairly far, but not far enough to get out the building. But it does work. So this answers the question, right? Like, is it live humans and such? No, not really, right? So I'm gonna put that answer on Amazon when I'm done with this presentation. And it also turns out, right, like if you just tweak the frequencies up a tiny little bit, instead of acoustic or subacoustic, you go straight into the ultrasonic range, right? So, this is obviously useful for sending acoustic signals back and forth between computers with microphones and speakers, without using a speaker, of course. But this probably also piss off dogs. So this is probably a decent dog whistle, right? Which, I haven't yet tested because nobody would give me their dog for experimentation. But you do get two very distinct signals, one at about 27 kilohertz and one at about 42 kilohertz, right? Human hearing stops at about 17 to 18 kilohertz. So we're definitely in the ultrasonic territory. And the principle of this emanation is exactly the same, right? We're causing this thing to flip its GPIO pins, that's kind of a spoiler, but fast enough that the capacitors are actually humming and vibrating and causing this acoustic output. Just like what Shamir talked about in his paper, but much stronger. Now, this is not at all a new idea. In fact, in 1998, Marcus Kuhn wrote this amazing paper called Soft Tempest, right? It deals with exactly this, using software to induce compromising emanation to exfiltrate data. And he was mostly interested in ways of mitigating that through different fonts and whatnot, but it was contained in VGA output to the monitor. So for example, right, if you put this line in your Xconfig, your screen will show up with this kind of pattern, right? And that pattern would emit about, will emit a RF signal at about 300 kilohertz, right? And in fact, if you YouTube, I think something like Monitor Eliza, right? People have encoded entire songs and symphonies using this. It's really fun to check out. Now, when he first presented this, I was probably, I don't know, like 17 or something, right? But I eventually read the slides, and the last line of the slide, the last two words of this, right, made me really think. He said, this is obviously a good idea, it's very interesting, but very much of it, or very little of it, is discussed in open literature, right? So you can figure out what that means. And then nothing happened for about a decade. So nobody followed up on this work, not really. And very recently, we had a series of papers dealing with basically follow-ups of using intentionally induced compromising emanation to exfiltrate data. The first one that I want to talk about is Bit Whisper. It uses thermal variations to get anywhere between 1 to 8 bits per hour, right? And its effective transmission distance is about, I think, 40 centimeters. So it's probably a good academic paper, but not very useful, right? And a second one talks about acoustic coupling, bidirectional communication. And there you can do a little bit better. You can get about 19.7 meters, right? And at about 20 bits per second, which is much, much better than 8 per hour. And the third one is kind of cute. So the authors took what Marcus Kuhn did about monitor RF emanation and picked that up using cell phones that had an FM receiver. So that's kind of cool, right? And over there, they were able to get about 7 meters and up to 60 bits per second. So what is the obvious next step in this line of research? First, we should generalize and unify the methodology for transmission, right? So instead of just causing acoustic emanation or RF emanation in a monitor, we want to generalize the principle of this all, so we can run it on every single device. And we want to minimize the hardware requirements necessary. So we don't want to depend on a specific VGA card or a specific sound card. We want to be able to do this on pretty much every embedded device out there, okay? And this is where Funtenna comes in, okay? Funtenna 101. Let's say you have your thing, right? And suppose somewhere on this thing, we have a pin that is an output pin that puts out a binary 1 or a 0. So as a software person, right, what you can do is set the logic state of this pin to be 0, 1, 0, 1, 0, 1, and what you would expect is a square wave, right, if you put it in the oscilloscope of 0 to 3.3 or whatever your voltage is. Now, this is where me, the software person, says, okay, so all I have to do is some RF magic, right, and translate that square wave into RF signal, then I'm done, right? And we win, and we get RF emanation. So this is what I did, okay? Advanced SDR. Do some, do some homework, learn some math, and that turned out to be super not productive, right? And then a little bit less ambitious, let's just talk about like how do radios work? You know, what does a RF wave look like, right? Forget about that. You know, and then let's, right? Electrons, like what is that? How does it work? You know, but okay, so we can actually do something here, okay? I remember my high school physics, right? Maxwell's equations, the top two basically will answer all of our questions there. Okay, so take your thing, take your pin, right? If you're running current through that wire, let's say electrons move through this wire, right? What happens is that current will induce a magnetic field, right? Remember the thumb rule, right? And then what happens after that is that magnetic field would induce an electric field and so on and so forth, right? And this is what we call electromagnetic emanation, right? And if we do this at the right speed, we get the right signal, and then we can receive it using, you know, something like an SDR or an AM radio or whatever it is. So here's the theory, right? If we can change the frequency of the bits going from 0 to 1, that's something we control, then if we plot this on the frequency domain, we should definitely see an RF signal of that frequency, right, of some intensity. And in an ideal world, we should also see some very weak harmonics, right, at very predictable locations, logarithmically spaced apart, okay? Now, that's the theory. Part two of this theory is, okay, so if we can do this, let's look at some of the most ubiquitous mechanisms we find on system on chips, on embedded devices, right? First one we looked at was PWM, pulse width modulation, and also pins that are responsible for GPIO, so general purpose input output, software control pins that could either act as input, right, for buttons and such, and output for, you know, lighting up LEDs and things. And the third one we looked at was the UART, basically the serial port, you know, maybe we can do something there. So here's where we did a lot of science, okay? So for each of these types of pins, we wanted to answer this question, okay? What are values that are possible for the frequency we can flip these things? So basically, how fast can we flip PWM, GPIO, and UART, okay? And the second question is, you know, what is the optimal value for flipping these pins, right? How fast should we flip these pins? And of course, there's also the third question of, you know, what length of radiator, so the antenna, right? Right here, we're not gonna have an antenna, but, you know, we're gonna have tiny little wires on the circuit board, let's say. What length of antenna is best? Or what length of antenna just straight up won't work, and what antennas will do the job to what degree? So here's our experimental setup, right? We made just a terrible Faraday cage that didn't work very well, but it was enough for this experiment. And this is where we couldn't afford, right? Like, you know, the maternity panties, right? We had to get just sheets of copper because otherwise it would have been way too expensive. And we used the Bus Pirate, we used the GPIO, you know, facility for the Bus Pirate to basically flip these pins at predictable rates, and then we measured the signal to noise ratio, right, of each one of those experiments, and we received the signal using a standard USRP2 with the basic RX board. And the nice thing about the basic RX board is it will receive frequencies at a very low range. So it goes, I think it goes anywhere between 1 megahertz to about 250 megahertz. Okay, so here's, you know, one data point that we gathered, for example. Given a 30 centimeter radiator, right, when we flip the pin at half a megahertz, 500 kilohertz, we observe a harmonic at about 2.5, right, that's expected. And we're getting something like, what does that look like, 17 decibels noise, signal over noise, right? And we did this over and over again, and we created this graph, right? So here are all of the antenna lengths and the frequencies of transmission and the signal strength that we were able to get out of it. If I have time, I definitely want to come back to this graph because you see these lulls, right? Like these low areas. They fall directly on lengths that you would expect to have. It's a small fraction of the perfect antenna. So we're talking about like one stat thousandths of the optimal antenna length. And you would expect if you get it exactly right, your signal strength would be actually very high. But we found exactly the opposite. So this is a really strange phenomenon that I think I understand why that is, but what it says is Funtenna will work, and it's actually better to not have a perfect radiator length, right? If you're imperfect about it, if you're a little bit off, given the realistic ranges that we're working with, which is sub inches and sub feet, right? You want to be slightly imperfect. Being perfect is actually bad. So data analysis, right? What are the possible values of f, right? The frequency at which we can flip these pins, and what are the optimal values, and what is the optimal length of the radiator? The last one is just really simple. Basically, if you don't have a radiator, it won't work, right? So if you're talking about just the pad on the circuit board, it doesn't emanate at all, right? The signal is very faint. We weren't able to pick it up. And really, the longer the wire, the better, right? I mean, that makes sense. Bigger antenna, bigger transmission. So the next thing is possible values for F. The hardware we work with, right, it was pretty standard for your IoT or embedded device controller. And the PWM, we were able to flip it anywhere between 10 kilohertz and 4 megahertz. But on the pen and printer that we worked with, the PWM is set at 13 kilohertz, which is on the very low end of this. GPIO is very similar. We were able to flip GPIO pins at about 10 kilohertz to 5 megahertz, although in some modern processors, you can probably go up to 20, 30, 40 megahertz, right? And on the UART, if you really tried, you can probably get the TX pin to flip at 4 megahertz, although it definitely wasn't very reliable. So effective range there is probably anywhere between 100 kilohertz to just shy of a megahertz, right? Now, optimal value for F, right? That's an easy answer because you have to transmit, you want to transmit it around 120 to 205 megahertz. So how did I get that value? Remember this secret fort, right, that I drew before? It turns out it actually does exist, okay? This is on an Air Force base somewhere, or at least it existed in the 80s. And there was this really fantastic paper that the Air Force put out that talked about RF permeability of steel reinforced concrete structures, right? Very useful. So let's say you wanted to Funtenna out of a 2-foot thick steel reinforced bunker, okay? Their findings say exactly this, right? You want to be able to transmit above 100 megahertz because below that, your induced magnetic field will be reduced, and above 200 megahertz, your electric field, right, induction is not going to do very well. So the sweet spot definitely is between 1 and 200 megahertz, right? That's exactly where you want to go. But obviously there's a problem, right? Because we can only flip these pins at about 5 megahertz. How are we really going to be able to get to the 200 megahertz range, which I will show you later. Okay, so all those things put together, right? Let's talk about generalized Funtenna algorithm. This is what you want to do. You take your thing, you take your pin, okay? And what you want to do is you want to flip this pin, turn it on, and wait a specific amount of time, and then you want to turn this pin off, and then wait a specific amount of time, right? And that's going to create this square wave on the line. And you want to do this at a predictable frequency, right? And you want to do this over and over again for a specific number of iterations that I call symbol duration. Okay, so a specific period of time. Okay, so if you do this, then you create something like this, which given what we talked about, will emanate an RF signal, which then you can use to receive and hopefully demodulate. But before you do that, you have to choose a modulation scheme. So we're going to try to approximate some very common modulation schemes that's easy to work with. The first one we're going to look at is amplitude shift keying, ASK. The second one is FSK, and the third, frequency shift keying. And the last one we're going to work with is on and off keying. And I say approximate because we're not really going to be able to do true FSK, for example, because the things we're working with are discrete values, right? We're not going to have continuous signal, right? So we're going to try to approximate this as much as we can. So amplitude shift keying, very easy, right? So all you have to do is flip your pins for a specific amount of time, right? That's going to generate an RF signal. And then you don't flip your pins for a specific amount of time. So this is a binary ASK, right? On and off. The problem here is timing has to be exactly right, because if you start shifting your sample, let's say you sample it right here, and then you start shifting, right? You're going to start missing bits because your sampler is not going to be aligned from when the 1 bit starts and the 1 bit ends, and then 0 bit starts and 0 bit ends. But it does work. So if you want to transmit 1010, just flip, wait a little bit, flip, wait a little bit, okay? The next one we want to talk about is frequency shift keying. So instead of just flipping your pin and then waiting and then flipping your pin again at the exact same frequency, what you want to do is flip your pin first at one frequency, then flip your pin at another frequency, right? And that's actually easy to do because all you have to do this is to change the delay values between, on and off, right? And if you did this, you get one frequency emanating and then another frequency emanating, back and forth. So this is sort of FSK for the RF nerds in the room, right? Yes, this is not technically 100% FSK, but it does work. So the third one that we tried is the one we like the most for Funtenna. It's called just simple on and off keying. So the demo that I'll show you later, right, we slow this thing down enough that you can actually see the thing on the screen. And if you took out a piece of paper, you can actually decode the information in real time, just to show intuitively what this all looks like. So a 1, for example, is a long duration of bits flipping, right? And a 0 is a short duration. And the nice thing about it here is you don't really have to worry about timing as much because you don't have to, the period of silence doesn't really matter. You can start by detecting a clock edge or energy high, and then you just wait and see how long that high signal lasts for, right? And then you can go quiet for an arbitrary period of time, and then you do it again. You're basically just measuring how long the signal is there. And long means 1, short means 0. And this is, you just repeat this over and over again to send out binary data. Okay, so that's the theory, right? Let's talk about Funtenna in practice. The hardware platform that we chose is the Phantom laser printer. It's the cheapest printer we can find. It even comes with a working USB cable, right? For $39, you can buy it on Amazon with free shipping. Like, we've been able to get this thing down to like $29 at some point. And this is a really great platform for experimentation because it's cheap. It is a very typical device created in the way that we create embedded devices and IoT things today, right? It's an ARM sock with a whole bunch of GPIO and a bunch of control circuitry that makes the printer a thing. But really, this is just a general purpose ARM computer with a bunch of pins that gives it IO capability. It does have IO, has a lot of IO pins. It has PWM, it has UART, and it has JTAG. So the JTAG is going to allow us to upload our Funtenna code easily and reliably so we can test it without going through a remote exploit, which we found one, but we're not even really going to talk about it because the software security posture here is terrible and you shouldn't be surprised about that. So remote exploitation is definitely possible, but that's not really what we're interested in here. All right, here's the board, right? So here's the sock, and if you see all of these pins, they're software-controlled input and output, right? So we can change the behavior of a lot of these pins just by changing software, which is exactly what we want. And the back of the board, the flash is there. And the sock, right? Not a lot of information about the sock, but if you look at the part number, this is the product brief that I found online. And here is a very typical structure, architecture for these ARM-based socks for devices, right? You have a processor, you have a bunch of I/O, you have I2C, serial, SPI, GPIO. And what's cool about this one is apparently this is an integrated laser printer sock. I mean, it's a very special purpose thing. It even has scanner control, fuser control circuit built right into the sock itself. Okay. Oh, and also it has Wi-Fi, but we're not going to touch that because if we touch that, that'd be cheating, right? So we're just going to pretend like the Wi-Fi chip doesn't exist at all. Okay, a little bit of hardware triage. This is basically a no-brainer, right? If you look at the board here, what do you think this guy is right here? Like, it's a UART, okay? And this 10-pin path thingamabob here is JTAG. So it took about half an hour for us to figure this out, right? Here's the UART pinout, and here is the JTAG pinout. And actually, I encourage you guys to get these things, get this printer and work with it yourself. We're gonna upload all of the code, instructions on how to play with the Phantom printer online right after this talk. And if you look at the console output, there are debug commands without authentication that allows you to set the target fuser temperature for warm-up and such. So you can really say like, set your warm-up temperature to 500 degrees, and it would happily say like, yes, boss, done, right? And I encourage you to play with that. It's a lot of fun. Okay, so the first thing we tried, Funtenna in practice, PWM, right? So there are a bunch of these PWM pins that controls motor speed, fuser temperature, power production, et cetera, et cetera. But the sad news here is we got no love from this, right? And this actually does line up with the data that we collected, right? If you're flipping at 13 kilohertz, you're not going to get a lot of RF emanation, right? But we were able to get some acoustic emanation by manipulating the actual hardware mechanisms that these pins control. So let's move on to something more interesting, okay? We have GPIO, and in fact, this thing has a whole lot of GPIO. There are 4 banks, right? A total of 121 pins. That's a lot. So there are bank A through C that has 32 pins each, and bank D has 25. And what do these pins do? So some of it is connected to things like buttons, right? These are inputs. And as an input, this is really attractive for Funtenna because what that is basically a wire attached to GPIO that runs about the length of, from this processor here to this button over here, right? Which is a couple of inches at least, right? To a thing that is either grounded or not grounded, depending on whether you pressed it or not. So if it's not grounded, can you hear me? So if it's not grounded, did my mic go off? Can you guys hear me? It's off. Hello? No? Should I just talk super loud? Is this good? All right. Okay, so the pins for input, right, has this long wire, which is really good for transmission. But the problem there is generally what you find is a debouncer circuit, right, at the end of input pins, which will really slow down the rate at which you can flip these things, right? Because there's basically a capacitor that that pads how fast the logic level can go from high to low, right? But there are all sorts of other pins, the output pins that controls LEDs, engine control, power control, toner power control, fuser control, and lots more. So we still have things to work with here, right? So the big question is, out of the 121, which pin do I flip, right? Do I go through one at a time and see what happens? No, because we want to emanate like a boss. And how do you do that? You just flip every single pin all at the same time as fast as you can. And then you see what happens, okay? And it'll either work or not work. Maybe the thing will catch on fire, it didn't, but let's just do that. No, all right. The revenge of embedded devices. Okay, cool. So a little bit of reverse engineering to figure out exactly how the GPIO on this chip works. It's very typical of embedded stocks like this type. It's just a memory mapped register, right? And if you write to OX20 from the beginning of the GPIO region, right? Every bit in there turns the specific pin off. So this is a memory mapped register area for bank A. There are 4 of these things, right? And if you want to turn a pin on, you set that specific pin to 1 at offset 0 is 24, right? So 32 bits, 32 pins, just flip the pins you want, write it to the right memory address, and there you're done. Now, Funtenna code in practice, this is all it took, right? First, we set up the addresses for GPIO banks, then we load it up into our registers, and we're just gonna forget about function calls and anything like that, right? We're not gonna abide by calling convention, because we don't have to. And then we're gonna turn all the pins on, right? And then we're gonna turn all the pins off. And then we're gonna do this over and over again, okay? And we're gonna do this at about 5 megahertz, right? So that's as fast as we could do this. And when we did this, things got really interesting. So I'm gonna show you some videos of what that actually looks like. Instead of a single pin in a controlled environment, we're talking about hundreds of pins in unknown PC board, doing all sorts of things, turning all sorts of power on and off at about 5 megahertz. So, right? What does that look like? So the first thing I'm gonna show you is all the GPIO pins going off at the same time, doing on and off keying, okay? And let's see if this video will play. There it is. Notice that we're flipping at about 5 megahertz, but GQRX we're receiving at about 9.8 megahertz. Okay? And that's not even the weird part. This thing goes all the way up to a few hundred megahertz, which is why I'm questioning whether I know how electricity works. But you can see it on the scope. This is it, right? So this is on and off, right? And notice also that the harmonic distribution of this guy, not periodic, not predictable at all. I mean, it's predictable, but it's not regular, right? And if we have time, love to talk about why that is. But how interesting, right? The signal is everywhere, and the harmonics are stronger as you get higher up in the frequency range in some places and not in some others. So that's what on and off shift keying looks like. I have no idea what the hardware did, but I'm flipping every single pin. I've reconfigured every pin to output, and I'm just flipping it 5 megahertz. And that's exactly what you see, right? So this is on an unmodified printer, flipping all the pins. And if I can do it on this printer without knowing what the hardware does, I can do it on another thing that has GPIO that I can turn on and off, right? And I'm not going to expect the exact same RF output or harmonic distribution, but I do expect to see RF signal emanating off of that device using exactly the same code, right? So that's what we're trying to do, generalize this mechanism so we can run on every device. Okay, so the next one we're going to do frequency shift keying. So this is an implementation that I wrote for the pattern printer. All the GPIO pins flipping at the same time, FSK. And let's see what that looks like. Do you guys see where the FSK is? Right, so you have one frequency, another frequency, one frequency, another frequency. So we're going back and forth, right? And the separation between these two frequencies at the harmonics, also not at all regular. So we have one here where they're very close together, and then we have one here where they're very far apart, right? And we have all sorts of different separation between the two, but it's just two signals, right, transmitting in this device. So that's what FSK looks like on this printer. Now, so that worked, but we weren't able to get the range that we really wanted because there was not a lot of radiator, not a lot of wire that we were able to take advantage of. So, I think we got, and we haven't really done a full-on range test, but we're talking about sub 2-3 meter, right? You can get this information out inside the room, but this is probably not, at least on this specific device, going to get you out of secret fort, right? Or even your typical office space. But the last thing I want to show is the UART. Okay, so there's a UART on this printer, there's a UART on your motherboard, on your server. There are UARTs everywhere on routers and all sorts of things. And if you don't plug a cable into the UART, like our data showed, you're not going to emanate at all, right? So that's not very useful, but people put serial ports on things for management. So let's pretend we actually connected a console cable to this UART. Let's see what Funtenna can do, right? So if you flip, actually, the easy test you can do is you just send the capital letter U, right, to the UART, you print it out, and that's going to translate to 010101. It's exactly 01 pattern. Manchester encoding is going to make that a perfect square wave, right? And if you put it on the O-scope, this is what you see, right? You have basically a square wave that works at about 250 kilohertz. It's not as fast as I like it, but this is a very simple thing you can do at home right now, right? 250 kilohertz, you should be able to pick that signal up with any modern sort of software-defined radio with an antenna like this, okay? But let's be a little bit more sneaky, right? Because it's probably pretty easy to detect a bunch of U's, right, going through your kernel down to the serial port. So let's see if we can do a little bit better than that, okay? So looking at the debug messages on the printer, we see that the UART is actually a DW APB UART.c. So I know the source code and the version. I also know the person who wrote this thing, but we're not going to talk about that. His name appears like 3,000 times in the firmware. So very simple Google search. If you just search for that term, you eventually come up with the actual data manual, right, for this UART. It's not a piece of hardware, right? This is a synthesizable IP block that people license from Designware that you can bake into your own embedded implementation. It's compliant with EMBA 2, and it's compliant with your standard console. What is it, 65502 console spec? Okay, and this is what the UART looks like. And the game here, right? We just want to flip this S out pin, right? That's the TX pin on the console, as fast as we want, as fast as we like, and we want to be able to control the rate and the duration in which we flip this one pin. That's all we want to do. So, reading the manual, this is what we do, right? My sneaky way of doing this. First step, you put the UART into control break mode, right? You basically set a specific bit in the line control register that tells the UART to stay high until you encounter a break signal, and then you go low, okay? Step 2 is we put the UART into loopback mode, right? So that's another bit flip inside another control register, right? Which keeps the, no, I got it backwards. Break means stay low until you hear a break signal coming from the receive end, and loopback means keep the TX pin high, okay? And then we're just going to set this back to 0 again, and then 1 again, and 0 again. And what happens here, right? This is all of the Funtenna code for UART right here. You load up the control register for the UART, and this will actually work not just specifically for this one UART. I think this will work for all of the 65502, UARTs, compliant UARTs out there, which is, I think, a lot of it. Basically, you set up your registers exactly right. One instruction, right, to turn the UART into loopback mode, which sets the TX pin high, and another instruction, right, to set it back low again, to get it out of loopback mode. So you're just doing this over and over again. Takes about 7 instructions, that's all you need. And it's very efficient, right? You can do this super fast. And you can flip those pins, the TX pin, at about 500 kilohertz without even overclocking the UART, which is also possible, right? So you can double this or quadruple it if you just change the reference UART clock, which is also pretty easy to do. Okay, so let's look at a demo, right? And this is where we're going to show a UART Funtenna operating at well, with 10 foot, roughly 10 foot of US console cable, or 10 foot of console cable connected to the UART. Okay, so we're gonna first do a live demo, and then we're gonna do demodulation of the signal, but I'm on stage and there's a whole bunch of wireless stuff, so I'm probably gonna fall back to the video of the demodulation, but I am actually at least gonna show you what the RF output of this guy looks like. All right, so here, we have a little script that takes the assembly, right? And then assembles it, locates it into the right proper virtual memory address, converts it into these super silly, just write commands for OpenOCD, right? Put it into OpenOCD and then boot the printer. So what I'm doing is basically hijacking the boot process, running my payload, right? So just to test Funtenna payload. And let's do that. All right, so I'm resetting over JTAG, OpenOCD, so I'm wiping an area, right, nulling it out to 0, where the load code is gonna, the boot sequence is gonna call, and then I'm going to upload my, I guess, 40 little instruction, Funtenna for UART code, right? And when we're done with that, we'll resume the printer, and the printer will start its boot sequence, jump to the Funtenna code, right, execute our payload, and we should see what we can see on GQRX. So for the data that we reported on our website, right, we used an EDIS-2 with the basic RX board, which is what I recommend you guys use, but for the purpose of the demo on stage, I'm using an EDIS B210, which can go anywhere between 40 megahertz up to, I think, something like 6 gigahertz. Right? But what we're really interested in is the lower frequency range. But I'm going to show you what this looks like even at higher frequency range. So imagine, before you see this, what you think you should see, right, on the scope, right? I'm flipping this thing at about 500 megahertz. It's going out a single wire, right? Think about what you want to see, or what you expect to see on this guy. And then we're going to see what we actually see. So I've resumed. Okay, look at that. Instead of one strong signal, right, and a few harmonics, this is what we're getting. This is at 40 megahertz, right? I mean, this is all over the place, and it's extremely strong, right? And I'm using this AM antenna, like AM TV antenna, that I soldered up to receive the signal. And let's see if we can get the signal at 41. It's there, right? The harmonic distribution is slightly different. You can see this banding here now, right? Let's go up 10 megahertz. Not there, right? 61, a little bit weaker. So let's go to our sweet spot, right? Can we do this, at bunker penetrating frequency range? Yeah, there you go, right? We're right exactly where we want to be. So 2 feet still reinforced concrete, right? This is the way to get out, right? We're exactly at the sweet spot. And I'm only flipping the pin, right, at 500 kilohertz. Well, what you see here is, RF emanation all over the place at, in this case, 131 megahertz, and this goes even higher than that, right? We have some theories of why that is and why this is so, spread out on the spectrum, but I definitely didn't expect to see this. Okay, so that's what the transmission part looks like, and if you watch very closely, right, this is just doing on and off keying. So a long duration means a 1, short duration means a 0. And now we're going to attempt to send an actual message out of this thing. So I'm going to show you a video, right? Because I mean, this thing looks pretty good, but it is directional, right? So it is does take a little bit of tweaking before you can get the demodulation correct. So let's look at this video that we made yesterday, right? So the setup here is what you saw in the first slide, right? We put it on a very large desk. The transmission is about, I don't know, 10 feet away, right? Or the transmitter is 10 feet away from the antenna. And this is us demodulating a piece of text in real time. Okay, so we're resuming the payload, right? It's starting to run. And all of a sudden you see here, right? This is Funtenna emanation signal. We put a preamble, right? So we can resync, right? I think after every 15 characters, just in case there's noise, distortion, et cetera, right? But this is the actual bit rate at which we can get this data out. And I think we can go, definitely more than 10 feet, and we can go much faster. The reason why we kept it at this rate is because I wanted people to actually see it, intuitively feel, what's going on here, and also experiment with how much farther we can push this mechanism. So that's why we've put all of the code, or we're going to put all of this code online with instructions of how to do exactly this, reproduce this experiment on the Pan and printer. It's super cheap. I hope you guys buy this thing, run this code, right, and start experimenting with this technique. Okay. Can anybody guess the last word? Do you know where this is from? Just shout it out, if anyone. Yeah, exactly. It's the first line of Neuromancer, right? Tuned to the color of a dead channel. There we go. So that's Funtenna out of the UART coming out of this device. And that's pretty much my talk. Oh, we're going to demonstrate this and also a lot of our embedded defensive techniques that we've built for routers at DEF CON on Saturday, right? So I definitely encourage you guys to come and play with this yourself. We're going to have the hardware there for people to actually play with, and also our Symbio code for Cisco routers. Not done yet. I received specific instruction to put this slide in. We have to learn something from this experience. So what do we learn? We learned that Funtenna works. We learned that you can do this type of data exfiltration without a radar gun and without an intern and without physical implantation. It's a good idea, I think. And I didn't show you one last thing. By the way, which brings me to point number 2. Network intrusion detection systems, right? The billions of dollars of technology that we have to prevent data exfiltration on known transmission mediums. It doesn't work in this case, right? It's not a substitute for embedded defense. I'm going to beat every network intrusion detector out there with an AM radio. Okay, so this is what we're going to turn on AM radio, and we're going to just scrub the band. Hold on. Right? That's what Funtenna sounds like on AM radio. And you're not going to find this on your firewall. You're not going to find this. So unless you wanted to. So unless you wanted to put a few thousand of these in different frequencies all over your organization, right, to detect this type of attack, right, which we, cooked up in 2 months and using about $1,000 of hardware budget, you need another strategy. How do we detect this type of exploitation, right? You can monitor every known or every possible transmission medium for data, right? You can monitor the entire EM spectrum if you wanted to. That would be very expensive. It probably may not work, right? Because we also get to choose our encoding scheme and such. Or the better way to do it is host-based defense baked right into embedded devices. Not just specifically for this guy, but for every embedded device out there. Because Funtenna you can't really see what Funtenna is doing on the outside, but if you actually had visibility onto the software of this guy, Funtenna is making this printer do all sorts of really weird things that it's definitely not supposed to, right? It would be dead simple if we had something like Symbio technology that I cooked up at Columbia University to detect this type of exploitation in all embedded devices across the board, to take this type of attack off the table, right? So we wouldn't have to worry about it. We won't have to use this, okay? And big thanks to all the folks that helped me make this happen. Chris Evans, right, on a horse. Joey Pantoga in the jungle, right? And I couldn't find Billy's photo, but Billy was the intern that cut open like 3 dozen of these printers and soldered J-type pins on it. So that was very important. And also right after this talk, we're putting all of the code for all of the demos I've shown on funtenna.org. It's going to be on GitHub. I really encourage you guys to check out this code, play with the printer, and see if we can push this technique even further and get bigger transmission, faster data rate, and things like that. So that's it. That's my talk. Thank you.